So today I'm going to talk about the title, Surgical Enhancement Using Electrical Bioimpedance to Improve Clinical Practice. So I teach an intermediate engineering class. It's basically surgery for engineers, and I start the class out the first day of lectures talking very briefly about the history of surgery, and it's kind of through art and archaeology is how that actually evolves. And I always start the class out by asking, so does anyone know what the first surgical operation, surgical procedures performed was? So I will ask. Say this again?
Tumor removal?
Not what my records don't show that.
Okay. Tooth removal. Tooth removal?
Tooth removal? That's not, I don't know if that's been documented.
I know about cesareans.
Cesareans were very early. That's actually the second or third slide on the presentation that I usually give.
Amputation?
That's always one of the suggestions as well, and that's very close, and that may have happened, but I don't know if it was documented that it was happened. Yes, I see some people, I think I saw someone pointing at their head. Yes, so trepanation. This is one of the first documented surgical procedures. And so when I say documented, people lived with this. So they actually found skulls, and it shows the wear marks on the holes that were put in. And this was from about 6500 BC. So this was relief pressure in the brain. And so surgery from there, in terms of art, and it's a little tough to see, but in 1875, this is a big jump, right? And so during these procedures, you can see everyone's wearing suits. They're holding the patient down because they don't have anesthetic agents right now. There's blood, and you can see it's not such an aseptic environment to work in. This progressed then to 1892, and in this case, we still have everyone's wearing suits, but here, the patient, this was ether anesthesia. It was the first time that the anesthesia was used, and the people in the audience were amazed. All of a sudden, this person didn't have to be held down, and so they were able to be operated on without worrying about the patient's pain level and such. Then we skip forward to 1929, and we start seeing something that's more similar to a modern OR. People are now not in suits. They're wearing gowns. They still don't have face masks on or head nets. The surgical instruments are actually, what we'll see, are very similar to what are used in some cases today. When we jump forward to 1945, this is Johns Hopkins, and we're getting much closer to a more modern OR. We have face masks. It's a more aseptic environment. We have headlamps over top the OR for the exam table. And then we come all the way forward now to, this was a few years ago over at DHMC. We see one thing, that the instruments are very similar in some cases. Everything in blue here is a sterile environment, so it's a very clean environment to be working in. And the surgeons are operating here. This is actually a tool that we developed, and they're probing the impedance in vivo of this patient here. Yes, this is Dr. Rick Barth here that's actually looking at a breast tumor with some impedance probe. And so surgery's evolved over the decades and centuries dramatically to the point that now we have robotic devices that we're able to actually operate on the person through a number of small incisions where tools go in and the surgeon sits away from this mechanism to control surgery. We have things called single port surgery where they actually make a small incision, they put a bunch of instruments into the abdomen, and then they can work and manipulate the tissues from outside the body. There's this big revolution in using image guidance. So this is a brain tumor, and they're trying to target where they want to take a biopsy or put a probe in here, and so they use different imaging technologies to help target devices. This is an example. They now, instead of having to open the body at all, they can use a needle-based approach to do a percutaneous radiofrequency ablation, which is just basically thermally ablating the tumor, or cryoablation, which is freezing the tumor. And this is an example where they use high-frequency ultrasound to treat prostate cancer through the rectum. And so what I'm interested in doing is developing technologies to basically enhance clinical perception and clinical procedures. through the use of novel technologies. And today what I'm going to talk about is I'm going to talk about one particular clinical application, one clinical field, and that's going to be prostate cancer. I've been doing a lot of work on that in the over the last 5 or 6 years. And the novel technology that I'm going to talk about is this thing called bioimpedance. And it's a measure of how the electrical properties of tissue are different for different tissue types and different pathologies, so benign versus cancerous tissues. And so I'll talk about my experience in assessing that in prostate cancer and in developing ultimately applications that clinicians will use to help improve clinical practice. So first I'm going to start off just talking about the problem of prostate cancer. The highest incidence rate of all cancers in men occurs in the prostate. About 230,000 men per year will be diagnosed with prostate cancer. There'll be 30,000 deaths associated with it. It's the second leading cancer cause of death in the U.S. If we look at the trends in general over time, so this is cancer death rates among men, you can see the prostate cancer is still the second, as we just showed in that previous graph. It's starting to decrease here with improvements in treatment technologies, basically, so we're better able to treat the disease. The incidence of prostate cancer, you can see this huge jump here back in the early 90s, and this happened at the advent of what's called PSA testing. So that's a blood test, prostatic-specific antigen test, that came on the market. And now we were having this huge influx of men who were being screened for prostate cancer. And so they were getting these elevated levels of PSA, and then they were being sent for certain types of treatment. And so that peaked very high, and now it's leveled out over the last decade and a half here. And there's a lot of controversy behind the whole screening with PSA. I'm not going to get into that right now, whether it's cost-benefit, if it's benefit to the patient or not. But that's kind of the trends that have been occurring. And then the lifetime probability of any man developing prostate cancer is 1 in 6. So it's a very prevalent disease, and it has a significant impact on many men's lives throughout the course of their lives. So I just want to run through the current clinical workflow of prostate cancer so you guys are aware of actually how clinicians look at prostate cancer diagnosis and treatment. And so typically what happens, a man is screened, so they either have a digital rectal exam or a blood test, a PSA test. If they're negative, they're good for another year, right? If they come out as being positive findings, then that means they typically go have a truss-guided biopsy. And truss is transrectal ultrasound. And what this entails is a man goes into the clinic. There's an ultrasound that is positioned in the rectum next to the prostate. And typically 12 biopsy cores are extracted. And those biopsy cores then are used to determine treatment strategies for the man. If the biopsy, or the truss-guided biopsy, if they don't find any cancer, so what actually occurs is 25% of men that go for a biopsy have cancer that's found, 75% have no cancer found. And so there's one of two things that happen in this 75% that are not found to have cancer. Either there is no cancer, and if that's the case, that means this screening way up here was wrong, right? So there's a false positive. If the other alternative is actually there is cancer and the biopsy just missed it. And the reason that the biopsy might have missed it is that they take 12 cores from the prostate. Prostate's about 50 grams or so, and with the 12-core biopsy, it ends up being less than 1% of the total volume is actually sampled. And so there's a lot of undersampling that takes place. For the 25% that are positive, now the clinician has to determine, okay, what do we do with this person? Do they need to be treated or don't they need to be treated? It turns out that 80 to 90% of men will actually die with prostate cancer, but not of prostate cancer. So determining which patients actually need to be treated is a clinical challenge right now. So if they do determine that it's significant, there's a number of therapeutic strategies. Men can go under watchful waiting, where it's basically they get their PSA and the doctor's just monitoring it more closely. Active surveillance, where they're getting biopsies more routinely. And then there's radiotherapy, surgical therapy, and chemo or hormonal therapy. And so prostate cancer, it's a significant problem, and there's a number of significant clinical challenges associated with it. And so my work has focused on looking at the electrical properties of tissue. So I'm going to run through the basics of bioimpedance and talk about how it might be useful in developing applications to aid clinicians in prostate cancer diagnosis and treatment. So the basics of bioimpedance. So the idea is we have some tissue sample, and we want to measure the electrical properties. And the primary electrical properties we look at are conductivity and permittivity. And the way you can measure that is you can send a current through your tissue, where the current passes through a set of electrodes that you put on either side of the tissue. You measure the current, you measure the voltage that goes across it, and Ohm's law, basically V equals IR. So you can pull out what your load is, the Z tissue here, by taking the ratio of the measured voltage and the current. And if you have phase-sensitive detection, you can get both the magnitude and the phase. So you can get the real part and complex part of the impedance. This measurement, it gives you a resistance and a reactance. You can relate this to the actual conductivity or permittivity of the tissue through a cell constant, which is related to how the electrodes are configured. In the typical case, you have this R equals rho L over A, where L over A ends up being your geometric factor. That is dependent on the electrode array. And so that's the basic measurement for how you would make an impedance measurement. And so what we're interested in looking at is if we take this set of electrodes and we put a piece of tissue in there, and we send a current through here, and we can send that current through at different frequencies. So it can, we range frequencies typically from like 100 hertz up to maybe 10 megahertz. And what you see, if you measure the impedance and you measure conductivity and permittivity, you'll see that conductivity increases in tissue with frequency, and the permittivity, which I am calling here, actually it's the radian frequency times the free space permittivity times the relative permittivity. It's the complex part of the conductivity here. This has a peak at some frequency and drops down. And so this has been found by empirically, originally people looked at these tissues and measured the impedance, and this is what they found. And so the question comes is, why do we see these type of spectral characteristics? So if we look at a single cell and we inject current through the cell, there's a couple of pathways that the current can flow down. So if we send a low-frequency current, we find that the current actually will pass around the cell membrane and stay mostly in the extracellular spaces. And this is because this cell membrane, it's a lipid bilayer, and it actually acts as a fairly large impedance to current flow. And it looks like a capacitor. And so at low frequency, we get current flowing around the cells typically. If we go to very high frequency, that capacitive nature of the cell wall actually becomes a short, and we're able to pass current through the cell. And so at some mid-range frequency, we get some interrogation of both interior and exterior components of the cell. And so this is interesting. So we can start looking at, if we can measure the impedance at different frequencies, we can start looking at things associated with intracellular pathology and things associated with extracellular morphology. So we can take this cell, we can model this as a simple 2RC type of model, and we can compute the impedance parameters here, and ultimately then relate our complex conductivity to a set of resistors and capacitors, where this resistor represents generally the resistance of the extracellular matrix. This resistance represents the resistance of the intracellular fluids, and then the capacitor here is the membrane capacitance. We can see if we plot conductivity and permittivity versus frequency, so we see some structure that looks like this, where we have some characteristic frequency that occurs in both the conductivity and the permittivity spectrum. And so one way of looking at the tissue is actually to look at in the complex plane. So I've taken conductivity and permittivity here. You can plot permittivity as a function of conductivity. And you can describe this arc as what's called, this is a Debye model, but so this is the complex conductivity. We have a high frequency conductivity, which occurs here. We have a low frequency conductivity, which occurs here. And we have a characteristic frequency at which we get this arc that's curving, right? And so what happens, though, in tissue is that we see slightly different structures. So we see this characteristic frequency occurring in the permittivity spectrum, but we don't typically see it in the conductivity. And this occurs primarily because we have cells that are not the same size, not the same geometry. So that capacitance term is actually distributed. It's a distributed type of parameter. And so what we can see is something, instead of this single cell type of curves, we see something that looks like this in multiple cells, when you have multiple cells within a tissue. So what Cole had proposed many years ago in the 30s was that you could add this alpha term to the denominator here. And this is basically a method for causing a dispersion in your spectral parameters here. And so what we see is that we still get this characteristic frequency in the permittivity spectrum. We still get an arc, but it's slightly depressed now instead of being a semicircle here. And then the conductivity has pushed over towards the higher frequency range. And so the whole goal, the whole point of doing all of this is to be able to look at the spectral characteristics of impedance of tissue that you measure, look at certain parameters, so conductivity and permittivity at certain frequencies, and these other spectral parameters. That is a way of actually decompressing a large spectrum of data. And so what we can get out of a curve like this is we can find these 4 parameters that are associated with this model, and we can also have discrete frequency components at conductivity and permittivity. And these are measures of the tissue morphology. So for instance, the high frequency conductivity occurs when the current is passing through both the extracellular space and the intracellular space. So it's a measure of both the extra and intracellular spaces. Likewise, the characteristic frequency is a measure of the cell membranes. And so one of the things we're interested in doing is measuring these values on tissue and seeing if they provide contrast so that we can use these to develop tools to aid clinicians in discriminating between cancer and benign prostate. And so what we're interested in doing is understanding actually how those individual spectral components correlate with morphological parameters. We're interested in developing technology to actually sense these in the clinic. And then we're very interested then in taking technologies and deploying them into preclinical studies, animal studies, and seeing if we can't ultimately impact clinical care. And then we want to translate medical devices. So I'll talk about a few devices in a moment, but first what I want to talk about is the potential contrast actually in prostate tissue. And so if we look at prostate tissue in general, there are 4 primary types of tissue that you'll find in the prostate. There's a thing called stroma, which is kind of the background tissue. It's largely acellular. There's high levels of extracellular matrix, high levels of fluid, and very few what are called epithelial cells. You have normal glandular tissue, and this is the primary functional units of the prostate. This is producing the fluids that the prostate produces. And this is made up of these glands. So these are these lumens, or these spaces here, these white spaces. They're ringed in epithelial cells. And the rest of the pink stuff in here represents stromal tissue that's throughout the tissue. There's another feature in tissue called benign prostatic hyperplasia, which represents basically as men age, they have this growth of epithelial cells. And so you get this larger increase in the number of glands. The luminal sizes typically increase, and you have these papillary structures associated with each of the lumens. And then the final thing is cancer. And here, it's a little tough to see, but all the section here is all these epithelial, they're very small glands, epithelial cells that are making these up. And so you can imagine that this is a lot of fluid with not as many cells. there's a large number of epithelial cells here, and this number of epithelial cells is increasing as we go up. Okay, so as we increase the epithelial cell concentration, basically, we're changing the pathways through which current can flow. And so we expect, looking at these different morphologies, that the impedance, the conductivity and permittivity should be related to these parameters, or related to these morphologies. And so we asked the question, so do the electrical properties of prostate provide significant levels of contrast for use in assisting clinical decision making? So what we did to answer that question was I spent a lot of time over in the hospital. I developed this small device here where we have this set of electrodes. We'd get prostates immediately after surgery. We'd take them up to the pathology lab. In the pathology lab, they section the prostate so they can look at them micrographically to assess them. We'd take each of these prostate specimens, place them inside our device here to measure impedance. We had these little pinholes in here, so we would put little ink dots so that we could co-register where we made our measurement and the tissue micrographs that the pathologist was going to look at. We put pins in the tissue. This whole thing was submitted in formalin and fixed. And so what we were able to do then is have this nice co-registration between our tissue morphology and our impedance spectra that we recorded. And so we did this for 50 prostates. We were looking at a frequency range from 100 hertz to 100 kilohertz. And we ended up looking at a total of 71 cancer specimens, 165 with BPH, 148 with glandular tissue, and 152 with stromal tissues. And those were the four main tissues we were looking at. And we had some small other tissues as well, but they weren't actually included in the analysis because of the small numbers. And so quickly want to say, how do we evaluate the sensor? And so I'm looking at ROC curves. And what ROC curves demonstrate is this is the sensitivity of your measurement and the 1 minus the specificity of your measurement. So this basically is the true positive fraction, and this is the false positive fraction. And what happens is you set a threshold on your device. So we would set a threshold on our impedance measurement, so the conductivity. And so we set a threshold, and we find out how many true positives we had, how many false positives we had, how many true negatives, false negatives. And we can plot that on this graph here. And if you have a perfect sensor, meaning that you've set a threshold that's perfect, you will have a curve that looks like this, closer to where there's 1 here, closer to this C curve. Something with B is a decent sensor, and then something with A is a 50% chance. It could be one thing, it could be the other thing. Okay, so ideally you want something that has more closely shaped to this C shape. And one way of then evaluating this is looking at the area under the curve. So if you have multiple sensors, you look at the area under this curve, and if the area under the curve is 1, it's a perfect sensing system. If it's less than 1, or if it's less than 0.5, it's not good, and if it's 0.8, 0.7, then we're looking at decent sensors. And so I wanted to show this just because we're going to show some ROC curves here.
What is ROC?
Receiver operating characteristic curve. So here's conductivity as a function of frequency, permittivity as a function of frequency, from 100 hertz to 100 kilohertz. Blue is cancer, green is BPH, red is glandular tissue, and gold is stromal tissues. And we looked at these different tissue types, and we found permittivity here. We had this very high contrast between cancer and all of the other benign tissues. If we look at the ROC curves associated with that, when we looked at it between the individual tissue types, between stroma and cancer, we had this 0.878 ROC, or AUC, area under the curve. So that's a pretty decent sensor, right? And so when we compared to all benign tissue, it was 0.8, which was we were happy to see those type of values as well. And then specificities and sensitivities are 70% sensitivity, and specificity was 70% for all benign tissues. So I wanted to introduce all those spectral characteristics because we were interested in looking at these individual values for cancer to see if they provided additional contrast. And so what you can do, we have this model, this Cole model. We fit this using a least squares estimation model to our data. So we had our measured data, which was sigma m, and we wanted to estimate the fit here. So we just used the least squares iterative approach. This is the data we were actually getting. So our curves were similar to these curves. Perhaps if we went to higher frequencies, these curves would have closed down completely. And so that's one thing we could think about exploring, is going to higher frequency ranges. You can see, though, these curves are different. And when we looked at all the data cumulatively, we found that the spectral parameters that we actually extracted were significantly different for 3 of these parameters. So this characteristic frequency, we had like a 4-fold contrast. So the contrast levels were very high. So this is kind of, it was exciting for us to see this because, if we can get this type of contrast in actually a device that we put in the clinic, we could definitely impact clinical decision making. And so you can see the AUCs, for instance, were up at 0.821. We had specificities and sensitivities at 70% sensitivity. We had a specificity of 81% for FC. And so we're excited about this. We compared this to other technologies. And so this is similar to those ROC curves, where a perfect instrument would have a value up in this top corner. This is MRI. PSA is that blood test I talked about. Transrectal ultrasound, and PET-CT. So these are different imaging modalities and blood test modality for sensing cancer. And you see where EIS falls in this range. And so it has slightly higher sensitivity. Specificity might be a little less. And so one thing you can think about is maybe we can augment these devices or apply EIS to some of electrical impedance spectroscopy to some of these devices to improve their clinical efficacy. So the last question we asked before we started looking at clinical applications is this idea of grading prostate cancer. And so there was that question mark over whether something is clinically significant or insignificant, right? And so that's a big question that doctors ask. And how they typically try to assess whether there is something that should be treated or something that should not be treated, they look at 2 things. They look at the volume of cancer. So if they take these biopsies, they look at how many cores actually had cancer in it and how much cancer was there. The other thing they'd look at is the morphological pattern. So it's something called the Gleason grade of the cancer. And there are 5 grades associated with prostate cancer. And these are the luminal spaces, the lumens of the glands. And you can see that as they progress through low-grade cancer to high-grade cancer, the lumens start becoming compressed. The cells actually start to bleed through the rest of the tissue, and you just have, instead of these formations of lumens, you have this massive epithelial cells everywhere. And so we looked at this, and these are morphological differences, and we thought that, hey, the impedance properties, because they're so dependent on morphological differences, may be useful in discriminating the different grades of cancer as well. And so we took that data set that we had, so we had 71 cancers, and we looked at the grades, so we had them graded. And here what I'm plotting are the different grades. So this is grade 6, 7, 8, 9. These are the different electrical properties. And we saw significant differences between grades of, say, 6 and 7. So a grade 6 and a grade 7. So 7 is considered kind of mid-level. 6 would be considered fairly low grade, and then above 7 is high grade. So if someone had a grade 8, they would be treated for something. If they had 7, it would be more questionable. If they have 6 or lower, they would likely be put on something like watchful waiting or active surveillance. And so if showing a difference between 6 and high grades will be potentially helpful in actually discriminating clinically significant from clinically insignificant disease. And so we were excited about this finding. And we're hoping to use that ultimately in some of the clinical applications that we're developing. And so now I'm going to actually get into those clinical applications. And so we're looking at what we can do to actually help clinicians better diagnose and treat men with prostate cancer. And so I come back to my primary flow chart of the clinical workflow of prostate cancer. And we look at here and we say, okay, where can we intervene to impact clinical practice? Because that's ultimately what we want to do. And so, one of the big targets is this trust-guided biopsy area. So the biopsies I mentioned sample a very small volume of the total prostate. And so if we could improve the biopsy yield or improve the volume of tissue that we sample, we may be able to improve ultimately the how clinicians decide who needs to be treated and how they need to be treated. So diagnosis and treatment is based largely on biopsy findings. There's been a finding that post-op Gleason grades, so that grading system, and the tumor volume, they correlate with disease stage. Okay, so the Gleason grade after prostate surgery and the volume of cancer will correlate with disease stage. 1 in 4 biopsies actually find cancer. And there's this finding that 43% of pre-op biopsies, so they grade those 12 cores, 43% of the case, 43% of the time, those grades are different than the grades that are assigned to the prostate after it's been taken out. And so that means it's either over or undergraded. And if it's overgraded, that means perhaps that man did not need to have surgery. And if it's undergraded, that may mean that perhaps another treatment strategy would have been more optimal. And so a single biopsy core samples a small volume of tissue, and it's about 0.5% of a full prostate. So how does this biopsy work? So a biopsy needle is typically, it's 2 elements. So you have this inner element with a shelf on it. You have this outer element, which is the cutting needle that comes across. And these are stainless steel, typically. And so if this is our tumor here, what happens is that inner element goes forward, this cutting element slides over it, and you get this small biopsy core that sits right inside there. And that's ultimately extracted, and they look at the biopsy core microscopically. And so I see these 2 pieces of metal, and we thought, hey, what I could do is if I insulate them from each other so they're not in contact, we could measure the electrical properties at the tip of the needle. So what we did was we put some polyamide coating on the inner needle and the outer needle, and now we have these 2 electrodes that we can connect up to an impedance analyzer, and we can measure then the impedance right at the tip of the biopsy needle. Okay, and so before we did that, we did a bunch of finite element sensitivity analysis to look at the geometry of the needle, so how large the electrode should be. Ideally, we'd have a larger electrode. As we get smaller electrodes, there's this thing called contact impedance, and if we have a larger electrode, the contact impedance decreases, and we're able to get a more accurate measurement of the tissue. So we did some finite element analysis where we basically changed the volume of the mesh in which we're looking at, and we found where the volume starts changing. And we saw that we get a sensitivity away from the needle of about 3 millimeters. Simulations, we saw 5 millimeters. Experimentally, we saw 3 millimeters. And then transverse sensitivity, that's the sensitivity away from the tip of the needle. We were seeing that at the tip of the needle, we didn't get a large measurement at the very tip. And so what we're trying to do is look at the volume around the tip that we can measure. And if we define this volume as some ellipsoidal volume, we find that with those sensitivity measures, we sample about 150 millimeters cubed at the tip of our needle. If we compare this to the 19 millimeters cubed, we end up sampling about 15 times more tissue than the biopsy alone. And so this is, we're sampling a heterogeneous tissue sample here, so we're not sampling single cells. And so there is things we have to take into account there, but it's sensing a much larger volume of tissue. And so we developed these needles, and here's an example of this needle that we developed. We got prostates after surgery, went up into the pathology lab. We built a tank. We filled the tank with saline. The prostate was sitting in here. We had an ultrasound probe so we could image the prostate. And this was basically simulating the clinical biopsy procedure. We took 12 biopsy cores. We would get the core out. We would have these analyzed by a pathologist. We would compare our impedance measurements to this device. And so this is the first step in actually getting to a device that can make its way into the clinic. So we wanted to do this ex vivo study to really understand how effective our device was. And so primary findings, we have the resistivity as a function of frequency and the imaginary component of the resistivity as a function of frequency. We see that cancer had a larger value than the tumor tissue. We see that the AUCs 0.77 and 0.79 for this device. And so our primary findings then are, so there are significant differences between cancer and cores without cancer. Sensitivity were 72 and 78, or specificity was 78%. And so the potential impact of this is, we ultimately want this to provide real-time feedback to the clinician. So if we can assess in real time if there is cancer or suspected cancer in a location, then the clinician can go in and take an extra biopsy core or two. Or the other thing is that if we get this extra information, now they have the trust data from transrectal ultrasound, they have the biopsy data, and then they have the impedance data. And so they can start developing these techniques to figure out, okay, based on all of these data sets, we can look at what type of treatment strategy is best for this patient. And so right now, things we're working towards to getting this more translatable are embedding the hardware. So we had a device that actually was tethered to a benchtop impedance analyzer. So now we're looking at embedding the hardware within the sensor. And then also we're looking at, right now we have these 2 electrodes. We're looking at expanding the number of electrodes on the biopsy needle so we can actually measure along the length of the core. So that was application 1. Application 2 is going to still focus on this truss-guided biopsy region. And what we wanted to think about was to see if we could enhance transrectal ultrasound in some way. And so if we look back at this relationship here, we see EIS is up here, we see truss is up here. If we can combine both of these together, we might be able to move this device up into this region over here, which is more ideal. And so to do that, you can actually, instead of doing single point measurements, as I've been showing right now, you can actually image bioimpedance by putting a multiplicity of electrodes around the organ that you're interested in imaging. And so this is just an example of what you might do if you have a number of electrodes around some object. You measure the impedance through multiple pathways. You build a model of your geometry that you're exploring. And then you solve using some EM, electromagnetic-based models, and finite element method, and you can produce an image of the conductivity or permittivity. And so before I got working in prostate, I did some work in breast cancer, and we developed this device here that measures impedance around a circular object, and there's a number of electrodes that are placed. We can generate these 3D volumes. We are looking at breast cancer here, and then we can produce conductivity images. And this shows there was a tumor in the lower quadrant here. And so this was some breast stuff that we did, and so we wanted to translate this over to prostate. And so in prostate, what we have here, this is a transrectal ultrasound probe. And so this is inserted rectally, and it produces images of the prostate like a bread loaf, basically. So you can produce these axial images of the prostate. We constructed a flexible electrode array, which we interfaced around the ultrasound probe. And so what happens, this window right here is where the ultrasound sensor actually propagates its pulse. And so this was basically our acoustic window. These gold things along here are our electrodes. This was placed on our ultrasound probe. We developed a system then that we could take into the OR, and so this is our EIT system is down here, monitor for viewing, an articulating arm. And so we took this into the OR, and we measured, I'll show you the OR in a minute. So first, what we do with this data, right? So similar to the previous examples I just showed of the breast, right? So we produce some volume, and we're using a cylindrical volume. We model the actual mesh of the ultrasound EIT probe, so the transrectal electrical impedance tomography probe, inside our mesh. We get our ultrasound data directly from our co-registered ultrasound. We can segment the prostate and then produce a volume mesh of the prostate. We can take that, embed that then into our big global mesh where we have our transrectal ultrasound probe and we have our prostate in there. And we can solve this electromagnetic field problem. So we developed those technologies, and then we took the system into the OR, and patients prior to undergoing surgery, they were sedated, and we basically used our device to both image their prostate with the ultrasound unit and with electrical impedance imaging. We recorded data. The prostate, what was nice about this patient population is the prostate was taken out after surgery, sent to pathology, and it was sliced. So we got these slices. And the pathologist then would create these maps where we defined where cancer was located within each of the sections. And so the goal was to then correlate these maps, where cancer was, with the pixels that we obtained from our electrical impedance images. So examples are shown here, where we have, these are our conductivity images for 2 patient cases. And we see this is those maps that I was just discussing where red denotes cancer. These are the actual micrographs, and you can see the cancer is actually circled in green on these cases. And these were the ultrasound images that we saw. And so what we found was we saw this increased conductivity associated with the location of cancer in these images, and likewise we saw similar features here. There was a question, I presented this yesterday, there was a question about why we see some erroneous data kind of on the ends a little bit, and we lose sensitivity on the ends, and I think what we'll ultimately end up doing is just using, and we lose that sensitivity because our electrodes are at the end, and so we don't have this cross-prostatic current that we're flowing in those positions. So we'll probably end up looking at a subset of this data as the more optimal data. But we analyzed these data on a pixel-by-pixel basis. So we took a pixel in our conductivity image, we took a pixel from those cancer maps, and we correlated to see if they were, in fact, had an elevated conductivity or not. And we looked at that, and we found that the conductivity of cancer was significantly greater than the conductivity of benign pixels. So 70% of our cases actually exhibited this feature where conductivity was higher. 30% actually exhibited the feature where the region where the cancer was, it was either iso or hypoimpedance, so it was either the same or lower impedance. And so this is actually similar to TRUS. So transrectal ultrasound, one of the findings is that, most disease is hypoechoic, but about 30% of the cases, it's either isoechoic or hyperechoic. And so one of the things we'd like to explore is, why do we see these differences between different cancers? Is it different cancers? Is it something with the electrical impedance system? And so those are some of the things we're looking to explore. So we're hoping that this would actually, what we envision is, someone going in to do a TRUS-guided biopsy, and they have this switch that they can turn on electrical impedance. And so I don't know if you've seen, so Doppler imaging is a way that they have ultrasound, they turn Doppler imaging on, and you can actually see blood flowing. And so we would envision something where we have grayscale TRUS, which is those gray images, you flip on the switch and you get conductivity images. And this might then guide them to actually do selective biopsying to improve the biopsy yield. And then we also might be able to use this information after the case, too, to look at Gleason grades, for instance, and see if we can better grade cancers. And so I want to talk about one more application that we're exploring, and this is involved actually with surgery, so the treatment of prostate cancer and how we might use impedance to aid in that activity. So prostate cancer surgery, what happens is a man goes in and they have that robotic device I talked about, comes up to the patient, they put 4 holes into the belly, and the surgeon operates and pulls the prostate out. So they cut around the prostate, and the rectum is on the bottom, the bladder's on the front, and you have the urethra on the other side. And so they pull that out, they sit the prostate off in the abdomen, it just sits there for a while, and what the surgeon does is he comes in, he takes the urethra from the bladder and the urethra from the apical end, sews them together, and then the robot comes off, they take the robot away, they finally take the prostate, which was put in a little plastic bag, and they pull it out of a hole in the belly. And then they send it off to pathology. And so the problem is what they do in pathology then is they slice it up and they look at the margins. And if they find cancer on the margins, then that man has to undergo either some postoperative radiation therapy or some chemotherapy. And so what would be interesting, and so what they find is if someone has a positive surgical margin, meaning they have a margin that has cancer, they have a much shorter progression-free survival. If they have negative surgical margins, meaning they don't have cancer, their progression-free survival is much longer. Okay, so the idea would be then is if we could somehow identify marginal regions that actually have cancer left behind during surgery, then the surgeon could, preemptively say, okay, I'm going to cut a little bit more tissue away. And hopefully then reduce this number of positive surgical margins and have a higher level of negative surgical margins. And so if we look at the numbers, so there's about 155,000 radical prostatectomies per year, about 15,000 to about 10 to 48% of those have some positive surgical margins actually associated with them. If you look at those numbers, 10-year recurrence rate is 50%, and so you end up getting about 7,000, somewhere between, it's a big range, 7,000 to 37,000. It depends on how someone's reporting their, or how a surgeon is reporting their positive surgical margin versus negative surgical margin rate. But somewhere between 7,000 and 37,000 recurrences per year after surgery. And so the primary regions that we get these positive surgical margins, this is the apex of the prostate, the base, the anterior, so the rectal wall there, and then this is the posterior. And so the apex here is the most prominent location where these cancers occur, or these positive surgical margins occur. And so, okay, I just wanted to show you, so this is what it looks like during prostate surgery. The robot comes in. We have a number of holes here where those instruments come in. This here is called an auxiliary port, and so it's about an 11 millimeter diameter hole that a surgeon, assistant surgeon, can actually insert instruments into, for instance, sucking out fluids or just aiding the surgeon in doing things. And the surgeon in this picture, well, actually, the surgeon's over here in this corner, as far away from the patient as possible, I guess. And so they don't scrub in, they just come in, they take their shoes off, and they sit at this console, and they manipulate the robotic arms. They have this nice visualization. So one of the key things about this is the visualization that's provided to them. So they have, through one of these ports here, there's a stereo endoscope. And so what that is, it's a scope that goes into the abdomen. It has two apertures. So you're actually seeing with binocular view. And so the surgeon sees a right and a left eye, and they're able to then see within this console a three-dimensional view of what they're working on. And so that's actually aided, the surgeons are very excited about that technology, so they can now actually operate from far away, it's minimally invasive, and they get this three-dimensional view. And so what we're trying to do, or what I'm trying to do, is develop a technique that we can insert some probe that uses electrical impedance, and we can basically look at the margins, so we can paint the margins, probe the margins, and try to figure out if, hey, this margin in this area looks like there might be some cancer here, so maybe we should do something about that. So what we've developed is, so the idea is here's a port, and we want to basically have an impedance analyzer and insert some probe into there. And so instead of just doing an impedance measurement, what we've opted to do is actually try to do some, what I'm calling microendoscopic electrical impedance tomography. So we have this small electrode array. These are approximately 700 microns in diameter to a millimeter in diameter. This is embedded within a silicon tube here. And the idea is this silicon tube then will be put in through this auxiliary port, and we will probe the prostate. This project is just getting going, and we're working on this. The vision that we have is that what a surgeon sees is something like this. And the idea would be that we would take this probe, we would interrogate different regions in the tissue. We would then figure out, based on our threshold calculations, if the region probed was cancer, if it was benign, or if it was in that gray zone, it was questionable. And so we might then overlay directly onto the surgeon's field of view what our EIS-based diagnosis is. And so far what we've done with this probe is we've characterized it slightly. So we've taken it and looked at its sensitivity of depth, and we basically put it into a saline bath that has a certain conductivity associated with it. We have a high impedance structure, and we basically can move the probe away from that. And if we do that, what we find is if we move from 0.5 millimeters to 1 millimeter to 1.5, our sensitivity is about 1.5 millimeters. So what we find is that means the probe is going to be sensitive to structures about 1.5 millimeters in. So the surgeon will be interested in knowing a little bit about the depth that the cancer is in there. And so this is just kind of characterizing the probe a little bit. We did some ex vivo studies on some porcine data. And this is kind of exciting in the sense that, that we're actually able to image things in electrical impedance tomography on this semi-microscopic scale, maybe semi-microscopic scale. So this is porcine tissue. There's a rim of adipose tissue here, a rim of muscle tissue here. Adipose tissue has a much lower conductivity, a much higher impedance. And so we have this circle here, and we rotated the probe, and we're able to see that the high conductivity corresponds to the muscle, low conductivity corresponds to the adipose tissue. And then we did one final thing, and this is I guess I was most excited about. We have this small streak of adipose tissue here, and we were able to actually see a high region of conductivity above and below the streak. And so what this is suggesting that if we have sufficient contrast, we could potentially image islands of cancer within a margin on the order of, 0.5 millimeter or so in diameter. And so this would be useful for surgical procedures. And so ultimately, this is what the surgeon's going to see. This is the apical margin. And this is a little tough to see, but this is what we were able to get out of the OR. This is a catheter that's coming in through the urethra. Patient's head is down here. And we would like to probe this area here, probe this area here, and then probe along the rectal wall here, and provide that information then back to the surgeon so they can make further decisions on whether they should resect more tissue or not. Our plans moving forward here, we have basically 2 phases. We're going to get 50 ex vivo prostates. So a lot of the stuff I've been doing, right, is we get these prostates after surgery, and we go and we evaluate the technology. And so we're going to look at these technologies by looking at the different margins on the prostate. We're going to try to determine threshold values that we can use for actually denoting cancer. Next phase is actually to do this in vivo, and so we're going to be making measurements during surgery of the prostate and the marginal bed. We'll also do the ex vivo studies on there as well to use as a correlative metric. And ultimately, that's not going to be used at this point for clinicians making treatment decisions, but down the road, once we actually are able to establish some thresholds, that's the direction that we're hoping to go. And so I just want to say, in conclusion, that the translational research studies that I'm working on and the program that I've kind of developed takes the process where we look at the bioimpedance and the contrast of tissue that's available. And then we try to develop technologies and hardware that is able to gauge that in vivo, ultimately. And then the idea is to ultimately translate that through animal studies, through human studies, and assess the potential of the technology in a clinical setting. So we're targeting diagnostic, treatment planning, and surgical therapy devices. The devices I talked about today, transrectal electrical impedance tomography, electrical impedance spectroscopy-based biopsy, surgical margin assessment based with EIS. Those are some of the technologies we're working with. We're using we're looking at a multitude of other applications for bioimpedance. This is the ones that are associated primarily with prostate. Opportunity to extend this kind of approach to other organ sites and pathologies. So we have lots of engineering, though, to further develop the technologies and to vet them. And then there's lots of clinical patient data to be collected and to be explored. So I will end there and acknowledge a lot of my clinical colleagues. This work is not possible without the assistance of surgeons, Dr. John Heaney and John Singh, our pathologists, Dr. Alan Schned, my faculty colleagues here, Alex, Keith, Andrea, a number of postdocs and grad students have been working on this project with me, funding agencies, and then, of course, the men that actually consent to participate in these studies are great. So we go up to them and we say, hey, we want to perform this research on you right before their surgical procedure. And most of them have been very receptive. And I've actually had the opportunity to talk at a lot of prostate cancer support groups around the Upper Valley and out in Manchester. And it's a really humbling and amazing experience to go talk with these men who have survived and are dealing with prostate cancer, and they're always so excited about the technologies that we're developing, because they really see them having an impact on, and not just their lives, but other lives as well. And so it's been a really great space to be working in, and hope to continue to do so. Thank you much.
So we have a few minutes for questions for Ronald. Who wants to go skiing?
So this is probably an issue of frequency range, and so I have the impression that the impedance monitoring technique, basically it's a passing current. What about scattering? Is that just the province of higher frequency regime than impedance monitoring?
Yeah, I don't think we worry too much about scattering at these frequencies because the wavelengths are much longer, and we haven't had any noticeable effect of scattering. So we model everything with a Laplace equation, so we actually kind of disregard any frequency-dependent properties of the wave propagation, except for the frequency dependence of the conductivity and permittivity. What we found in actually some early work that Nirmal Soni did we were trying to go to elevated frequencies, so we were going up to 10 megahertz. And we found that at 10 megahertz on a large, it was a breast volume we were looking at, 10 megahertz we had, I think it was, we looked at a Helmholtz type approach versus the Laplace approach, and I believe it was about 1% variation at 10 megahertz. I think for these small, and then that's dependent on the size of the volume that we're interrogating. I think for these smaller domains even, we could go to higher frequencies and we wouldn't have a major impact due to some of the higher frequency effects.
Well, and then a related effect is sort of the diffusion of the current due to the fact that the finite conductivity and the lump circuit model doesn't really take that into.
That's right, it doesn't. That is exactly right. And so for the imaging, so it is a diffuse problem, it's a nonlinear problem. We solve that using a Laplace equation. For the sensing device, if you're having just a bipolar type of measurement, yeah, of course, it is not just a single discrete parameter model. That said, it provides a good mechanism for at least looking at the data and parameterizing it in a way that may have some clinical benefit. So for instance, one thing that I'm interested in, so we take these probes, right, and we calibrate them, we put them in saline solutions, and we try to figure out what that geometry factor is, right, that R equals rho L over A, that L over A term. So if you have a different geometry, right, that L over A is going to change. And so that will also change depending on the conductivity and the properties around it, right? And so we don't take that into account right now. Right now we have we measure it over multiple conductivities, and we use an average geometry factor because of this distributed current. That's what happens there. And so that is something we could think about modeling. It depends on what the largest effect is. If the effect is larger due to that different diffusion, or if it's larger because of the contrast in the types of tissue. I think we're seeing that the tissue contrast, we believe, is the larger influencing factor there.
So have you done that same sensitivity analysis on I'm sure somebody must have done this, right, looking at the fringe fields. What's the effect of sort of a lump parameter versus a true, let's say, use Laplace equation and actually model
Yeah, so
distributed way
So what we did, we did simulations and experiments with that biopsy needle probe, right? And so the sensitivity in simulated world, so meaning the field at which it was sensitive to, was larger than experimentally. So when I took it to the experimental world, the radius at which the probe was sensitive to decreased. So I think there are differences. I haven't explored that.
Yeah, I don't know if anybody's done that.
I don't.
remember either. I think the effect is really smaller than the
I think so. I think it is smaller than that as well, but I think experimentally things are always a little different. Yeah.
Brian, I was curious, what kind of statistical methods do you use when you have multiple characteristics? Is it just a kind of multivariate logistic regression, or is it more like a parametric machine
So we've done some non-parametric, so testing for comparing some of the data. Usually when we're looking directly at comparing tests, so we do a lot of t-test, paired testing, and that's our primary metric for looking at differences between tissue types. And then
multiple metrics, haven't you?
so yeah, we haven't, so that's one thing that we haven't explored much, and I'm really interested in, so yeah, so I showed all these graphs, right, and it's always on a single parameter. And so I think there's, and so I think there's a lot of other information we could leverage by combining all of the metrics together to get a much, improved sensitivity. I haven't explored that space quite yet.
What kind of a resolution could you realistically achieve with your instrument?
So it's very dependent on the electrode geometry. And so if we have a ring of electrodes that are 10 centimeters in diameter, okay, we're going to get a resolution probably, for absolute imaging, probably, 3 to 5 millimeters, maybe we might get. As you decrease the size of the electrode, so the electrode array, so for instance, this small surface margin assessment probe, we're looking at being able to differentiate contrasts on the order of, probably 0.5 millimeter or so. I think so the other thing you can do is, so we're thinking about having arrays of electrodes, and so instead of just having this circle of electrode, if you actually have electrodes on the inside there, that's going to improve your resolution as well. The maximum, though, you're not going to get to cellular resolution ever with this, so I'm thinking, the absolute maximum that you will be able to get is probably on the order of 50 microns, 50 to 100 microns, if you get a very small electrode array with needle electrodes, for instance, or something like that. I think you could probably pull that out. Yeah.
So I have some colleagues that do microwave imaging.
Yeah, there's people here too, right?
People,
Yeah.
yeah. And well, the last conversation I had, they were claiming, microwave imaging has better resolution than impedance spectroscopy because back to Bill's point, because you can use scattering to get a signal, and that doesn't have to be restricted in the spatial region of your
Right.
electrode. I was curious if you had.
So I think.
Going into that direction, or.
So I would be happy to go in that direction. One thing that's difficult about microwave imaging is, so it's much higher frequencies. And so integrating those type of technologies into the clinic, at least some of the things that we're looking at, associated with cabling and things of that nature, I think makes it challenging to go down that route. You could think about, though, designing, embedded electronics that are much closer to the device that you're using. So yeah, it would be interesting to go down that route, and I haven't talked with Paul much about, prostate applications, but yeah, it would be interesting trying that route. So. Stu?
Yeah, I was just curious, you mentioned how your technique could guide the truss biopsy.
Yeah.
I was just curious, I want to understand, could you control where along the natural track of the truss biopsy needle you can take the skin?
So what I think, so when I say control or guide, I think basically we would set thresholds in our impedance images, and the idea would be it would show you where to sample, and then I think you could use either ultrasound or impedance tomography. So impedance tomography you can actually do very fast. You can do high-speed video rate imaging. So I think you could use either impedance or ultrasound. So ultrasound is pretty good at guiding a needle. It's real time. You can see needles going through pretty well. So I think if you could identify where you should be probing, I think either ultrasound or electrical impedance could be used to actually guide the needle then. So the surgeon guides it.
Would the truss probe actually slide along this long axis?
So yeah, it does. So yeah, so you actually, the needle comes in and you can move the needle guide basically up and down, and you can rotate it. And so that's, yeah. That's exactly right, yeah. So right now what they do is they have a prostate and they don't aim at all. They take 12, they do a systematic biopsy. They go 1, 2, 3, 4, 5, 6, and they've done studies with truss, and because of the lack of sensitivity and specificity, they don't get any better yield by targeting lesions.
Yeah,
and so,
there's no imaging method
That's right. There's no imaging method they can do in real time. Yeah. And so if they had something that was able to provide more accurate identification of lesions, then they could perhaps target those. And then the thing that's good about that is if you target cancer lesions, then the biopsy cores that they grade, the lack of concordance, there was that lack of concordance between surgical specimens and biopsy specimens. So if you're targeting those biopsies and you grade them, you might actually reduce that, you might get a more accurate grading of what's actually in the prostate. And so that would be the goal there.
I was also curious, is there any advantage in having a urethral electrode?
Yeah, so what I didn't show, one thing that we're looking on is actually taking the biopsy needle that has the electrodes on the end of it, combining it with our truss probe. And so now we have these, when we take the biopsy, we have these intraprostatic electrodes, and we have the electrodes on the surface. And so we could do that, for instance, 12 times or 6 times, and combine that intraprostatic data with the boundary data we're collecting, and improve then hopefully our resolution. But yeah, we have thought about doing a urethral one as well. The reason that you might, you could not. Right now, so the men are awake when they have this procedure done, and so giving them a urethral catheter as well as giving them a transrectal ultrasound. Yeah. So that's the grad students. If you're interested, that's yeah. So. Yeah.
Okay, great. Thank you for your time.